Okay, so we are live. Hello, everyone. Welcome to another session. So we have Admond with us today. He took the very first session of this boot camp on introduction to data science and its applications, and actually kick-started our data science learning journey. So it's actually one of the most popular and informative sessions of ours till now. Well, here we bring to you another interesting hands-on session. It'll be on artificial neural network. So I'll hand over the control to admin. You are good to go. You can start with the session. All the best.
Thanks, Kunika. Am I a host now? By the way, can I share my screen?
You're not able to share your screen.
Yeah,
right
you
now?
can. You can share
Okay.
now.
Cool.
Great. Okay, let me share my screen. Okay. Can everyone see my screen?
Yes, now we can.
Okay, hey everyone, great to be here again, and thanks so much for the introduction, Kunika. Really appreciate it, and great to be here again to the DeFi bootcamp on the neural network topic today. I'm really happy to be here today after the first session on the intro to data science. And yes, today we're gonna go through what's one of the most exciting areas in data science, which is the artificial neural network. And this session is mainly targeted on beginners. So if you are new, somebody who is new to neural network, or you're just curious about how these things works in a general sense, or just want to get a high overview or high level understanding of exactly how neural network works in general, I think this session will be helpful to you in terms of your understanding, right? So let's get started. So before that, let me just get this away. Okay. Cool. So just a quick one, a little bit about me, what I'm doing and my background, etc. So I studied physics in NTU in Singapore here. And currently I'm a data scientist at Micron, one of the semiconductor companies here. And also during my free time, I do write some articles, data science articles on different platforms, namely Medium or Towards Data Science, just to share about my learning journey, so my experience and even my mistakes with other people. And also I do a little bit of consulting on the side, and as well, I'm a data science communicator. This is why you are seeing me today, to share also my knowledge and my experience with you guys, with the students around the world, to really help them understand more about exactly what data science is in a broader sense, which is very exciting because I got a chance to speak with different people from different backgrounds. And I hope the session today will be helpful to you guys if you want to learn more about neural network. So what we're going to cover today, and in fact, today is not about me, today is about you, and today is about learning more about neural network. And it's very exciting because there are two main parts here today, and I'm going to show you the first one, which is what is artificial neural network? It's a simple question. A lot of people, especially for beginners like me last time when I started in data science, I was quite confused about the architecture, how it works, how exactly that makes neural network work the way it is, how does it really make prediction, how does it make it so exciting. So I was a bit confused at the beginning, but once I started learning, breaking it down into the most fundamental level on how exactly neural network works, I was able to gain a better understanding when it comes to my implementation. And I hope today you get the better understanding of neural network as well. And second, once we understand how neural network works and what it is, we're going to show you how to build a simple ANN or artificial neural network model for real. Right? We're going to do this in a Jupyter notebook, and we're going to show you how you can run this simple network as well on your PC locally by just getting some of the code and some simple data set to get hands-on experience. So it's kind of exciting. So in today's session, not just about conceptual learning, but also on the implementation part, where you get the chance, opportunity to first test and run the network yourself after this session. Right, so what is artificial neural network? A $1 million question, and I think this is one of the most common questions that a lot of beginners in this field, they tend to ask this, and they just Google search with tons of resources, and they got confused sometimes, at least for me, and they got overwhelmed by all the information out there, articles, YouTube videos, etc., etc. So today, I hope that this session will really help you get a better understanding of how this works. Again, let's look at the most basic and fundamental form, which is the building blocks of the whole neural network, neurons, right? On the higher level, if you look at the neuron this way, it is really just a neuron that takes inputs, which is your data set. Okay, and it does some sort of math behind it, which we're gonna go deep on how this math work really behind the scene. And finally, once the neuron has done some mathematics, behind the scene, it finally produces one output or prediction in our way of understanding. And this is really what we see on the surface, right? So maybe before that, before we even go further to the mathematical parts, let's really pull back the curtain and see what is behind the scene that makes neural network works. Okay, so the thing that I'm gonna do now is really to break it down into different parts of the neuron on how it works for all the components, so that you guys can understand how the whole neural network works later on, right? So let's pull back the curtain and see what it's in behind the scene. If you just remove the high level understanding, so if you really just look at the core parts of the neuron itself, you can see there are some of the very simple linear algebra, some of the very simple calculus. Really, it's just a multiplication of different matrices behind the scenes within the neuron. And again, you can see that if you just focus on the first part, which is the inputs layer. So from the inputs layer, you get your data set. So imagine now you are given a simple CSV file, right? And each of the column is your feature. So essentially, in this input layer, each of the neuron, or each of the X1 or X2 here, refers to each of the feature of your data set. And this feature, we have a value, we have a number, right? And this, after that, we'll multiply with what we call the weights. So again, you can see that X1 and X2 are your features in your data set. And we're going to do a simple multiplication by multiplying these with our weights. And before you ask the question what this weight means, essentially weights are something that's is a core part of the whole neural network architecture. It is the way, the approach on how neural networks learn. Okay, and by adjusting the weights later on for this neural network will decide what kind of signal is important and what signal is not important to certain neurons to pass on. And the higher the weights, the faster it will trigger the activation function. Okay, and I'm gonna explain a little bit more about the activation function here. But for now, we can just consider this as some sort of function for us to pass the value through. That's it. Okay, but here we really just want to focus on the meaning of what these weights mean, right? And the weight essentially determines what the neuron has to learn, what kind of pattern that the neural network has to learn from our data set. And the higher the weight it is, the more impact, all right, this will have on the network. So that means if you assign certain higher weights to certain feature of your data set, so this means you are telling the neural network that your feature, this particular feature, plays a higher role, plays a higher importance to learn the pattern behind the data sets. Right, so this is the whole idea of why we need to have the weight at the same time. Now again, just now we said that we want to multiply the weights with our input values. So what's the next step? The next step is gonna do the sum of the multiplication. So what we call a weighted sum. So the weighted sum here really means that for each of the feature value, if you just focus on the X1 here, for each of the feature values here, we're going to multiply this with our weights. It's called W1. Okay, and for the second second feature here, x2, we're going to multiply another weight, which is w2. And we're going to multiply these together. And finally, we add each of these multiplication together. As you can see here, we multiply x1 with our weight 1, multiply x2 with our weight 2, and we add them both together. And finally, we add what we call a bias, right? So what is bias? Again, what's the question? This is the common question. What's bias? On a higher level understanding, without going deep down, bias is really something that we use to delay the triggering of the activation function. So again, you can imagine that the higher the weight, the more easier it will trigger the activation function to our prediction. But the bias is something like a penalty. It's something that we want to slow down the triggering so that the activation function wouldn't get triggered so easily. So it's kind of like a balance if you think in this way. We don't want to trigger the activation function too early using this bias here. So this is something that the neural network has employed to learn the pattern behind the dataset itself. Now, once we have added all this multiplication, of your features with the weights, what is next? Simple. The next is really to compute them all together by getting these values, the weighted sum values, into a function. And this function is what we call the activation function. Now here comes the best part. The activation function essentially is some sort of function, whatever functions that you use. It can be as simple as a linear function, whereby in this function itself, you just input all the weighted sum that we computed earlier, which is x1 multiplied w1, x2 multiplied by w2, and added our bias. So this whole chunk of stuff, we're going to put them into an activation function. And this activation function will tell us whether we want to fire off to the next layer or not. So this activation function really plays an important role to see whether we really want to learn what kind of pattern for each of the neuron itself. So to break it down further, an activation function is really used to, in a technical way, to turn an unbounded inputs into an output that's a nice and predictable form. Now, if you look at the right side of the slide here, which is a sigmoid function, which I think a lot of us are familiar with. Imagine this sigmoid function is our activation function, right? And this sigmoid function is really for us to turn an unbounded input, right? An unbounded input means it could be from negative infinity to positive infinity, which is hard for the neuron to learn because there's nothing for it to bound the values together to give us a sense of how much the neuron has learned, right? In other words, activation function helps us determine how well the neuron has learned. And in order to do that, we need to keep it bounded. And to keep it bounded, we need to have some sort of functions. And sigmoid function is one of the activation functions that we use to keep the input bounded. And this will essentially decide whether a neuron should fire or not, right? Because in the neural network itself, we will have different layers. Each of the layers will have different number of neurons. And this neuron will determine whether it will fire the signal to the next layer of neurons or not, and so on and so forth. So the activation function here really plays an important role when it comes to learning some of the important patterns of our data set, right? If the pattern is not important enough for the neuron network to learn, it will not fire off, it will not trigger to the next layer, and this pattern will die down because this pattern doesn't really contribute to anything for the neural network to learn. So here, the activation function really says that it receives the value from the multiplication, from the weight. And this way is telling me that, hey, this feature is really important. You should trigger the next layer to learn, so on and so forth. And this activation function will talk with the weighted sum to see whether they will trigger or not. So it's kind of like a conversation, among multiple parties to determine whether they want to trigger the signal to the next layer or not. And that's it. Now that we have understood how a neuron works, right? But in neural network, we have multiple kind of layers and neurons. And this is where the whole network is born. A neural network really is nothing more than a bunch of neurons that are connected together, if you think in this way. right? So once you understand what each of the neuron does, how each of the neurons interacts with one another, if you just combine them together, it is just a bunch of neurons connected together, talking with each other, telling them what to learn, things like that. And that's it. This is how the whole idea of the neural network. It is a bunch of neurons connected together. And this kind of neural network can have any number of layers. It can have 1 layer, it can have 2 layers, 3 layers, or what we call the hidden layers. All right, it can have any number of layers with any number of neurons in those layers. If you look at this graph, right, this slide here, let's say I have an input layer and I have a hidden layer, and this hidden layer has 2 neurons, but you can add it up to 10 neurons or whatever number of neurons that you want. But just remember, the more number of neurons you add in, the more complex the neural network will become. And it depends on how complex you want your neural network to learn, right? Because the more complex it is, the heavier the calculation it is, and the more the neural network will start overfitting. So this is the whole idea of it. You determine the number of neurons, you determine the number of hidden layers, and essentially the whole idea is to use these layers to help you to learn the pattern from the data set and give us the prediction. So each of the neurons here learns different features. Maybe for the first neuron, if you look at H1 here, it might learn some pattern 1. It might say that if you want to predict house prices, maybe this neuron here learns that, the number of square feet matters a lot. So this is what it learns. Maybe the second neuron here learns that actually, the distance between your house and the train station matters a lot. And this is what the second neuron learns. So different neurons learn different features or different things. And the beauty of the neural network here is really boils down that it can learn on its own without us putting in any of our human assumption, which is the best part. You just put in the data and the neural network will just learn on its own without us interfering it. And this is why neural network is so powerful and so popular right now at the market in our current trend or our current industries right now, because you can just put in a lump sum, a chunk of data set, and a neural network can learn itself, some of the learning patterns of what kind of features that I need to pick, or what are the patterns that are important for me to output an accurate prediction. It is a good part of it. And usually how we do that is through the most fundamental neural network here, which is the feed-forward neural network. Now, what this feed-forward neural network here means that we put in the input here, we multiply the weight. All right, we go to the hidden layer, we trigger the activation function, and then we go to the output layer. The output layer is the layer where we output the prediction. And this one-way approach is called feed-forward neural network. Okay, but in order for this neural network to learn, we need to adjust the weights, which I'm going to show you later on. Because weight is the ultimate way of a neural network to learn. Different weights decides what kind of patterns, what kind of features that the neural network to learn. And in order to help a neural network to learn, we need to update our weights, right, in different iterations here. So here comes one of the most important parts here, which is how are we going to train a neural network? Again, there are only 3 main steps here that I would say. First step, the whole idea of training a neural network is really to minimize the error or loss from our predictions. Again, if you think in terms of the logistic regression way, in terms of other machine learning models that you guys have learned before, really neural network is to minimize the error from our prediction, okay? And by minimizing the error, the loss here, the neural network will have a better prediction, which makes sense, right? So here, how we're gonna minimize the error is through what we call a loss function, or some people may call it cost function, okay? And one of the most popular loss functions here is through the mean square error, MSE, which you can see here, the formula here, which really is the square of the difference between the actual prediction, the actual value and the prediction value. So ultimately what we're going to do is that we will have the input layer, hidden layer, output layer, we're going to run through the whole process, right? We're going to put in our data, okay, our data here in the input layer with the features value. We're going to multiply the weights for each of the feature, and we're going to fit in to the hidden layer here, where we're going to trigger our activation function. And this activation function will tell us whether what is the predicted values here in our output layer. Okay, and at this output layer, this is the crucial part, because this is the place, this is the stage where we compare the actual and predicted values here. Okay, again, imagine you are given a data set. All right, you have all the actual values. Okay, now here at the output layer, with what your neural network has learned, you have your own predicted values. Now you have your predicted values, you need to compare the actual and predicted values through what? Through a loss function. So this loss function with a simple formula here is going to tell us how much is the error. For example, if your actual value is 5, maybe your predicted value is 3, right? So a very simple calculation is 3 minus 5. So your difference here, your absolute difference here is 2. So our error here is really 2. Okay, and we're going to compute this loss function here and find the error. All right, so just say that you have the error calculated by comparing your actual and predicted values. What is the next step? The next step is to update our weights. This is the crucial part. Why do we need to update our weights? Recall that weight is how a neural network learns. All right, the weights of your neurons, the weights assigned to each of your neurons determine what kind of pattern that your neural network will learn. So your weight here is something that is so important that in order to minimize your prediction accuracy error, you need to update your weights continuously and your bias continuously to minimize the error from your prediction. So the whole idea here of updating the network's weights and biases is really to minimize the error from our prediction. And the whole process of doing this is backpropagation. Now the name here sounds a bit far-fetching or sounds a bit special, but essentially what we are doing here is really, we do the same thing, feed in our data to the input layer. All right, each of the neurons here refers to each of your feature value. You're going to multiply these with our weight, and we're going to sum this up for each of the neuron. And within each of the neurons here in the hidden layer, we're going to tell, and we're going to see whether this activation function will be triggered or not. Okay, if it is triggered, what is the value? And this value here is the predicted value in the output layer. Now, once we reach the output layer, we will have our predicted values, and we're going to do, again, the comparison with our actual value. And we're going to do a simple calculation using this loss function here and find the error. Now, once we have the error, what is the next step? We need to know what kind of weights that we need to update in our neural network in order to minimize the error. Okay? And the whole system of going back to the whole neural network to recalculate all the weights, to re-update our weights in the whole network is the whole idea of backpropagation. So this system here of calculating or updating the weights is through calculating the partial derivative by working backwards, all right, in our neural network. And this process is known as backpropagation. Now, there are two things here. The first thing here is that you just need to know backpropagation is an approach to update our network's weights and biases in order to minimize the error from our predictions. To further go deeper a bit, this backpropagation essentially uses a technique called gradient descent by calculating partial derivative by working backwards from our neural network. Now, some of you may not be aware of what the whole concept of partial derivative, right? I know this topic is a little bit technical. I would suggest you to go and look up a bit more of the partial derivative. Essentially, it is a core idea within the whole topic of calculus. And this whole technique of partial derivative is the whole algorithm behind the backpropagation to update all the weights within our neural network to know exactly what kind of weights that I need to update, what kind of weights that I don't need to update in order to minimize the error. And we do this by using this very simple formula here, actually not so straightforward. That requires heavy calculation behind the scene. If you look at here, this is what we call the partial derivative. So L here is your loss function. Okay, the W here is your weight. So for each of the weight here, if you look at this, each of the weight is your W1 is your updated weight. Okay, and for each of the iteration, meaning for each of the calculation here, once you have done the prediction, you compare the value and you backpropagate back to the network here to update the weights. This is considered as one iteration or one epoch, if you may call it. Okay, and this backpropagation is done by updating the weights according to how much they are responsible for the error. For example, in the whole neural network, just imagine you have 10 different weights. Okay, of course, each of these weights is responsible for the error in your prediction. So now the backpropagation is going to tell us among these 10 weights, what kind of weights, what are the weights that I need to update in order to minimize the error. Okay, so maybe the first weight is 0.1, maybe the second weight is 0.3, third weight is 0.7. Maybe some of the weights causes the error of your prediction, and using the method of backpropagation is going to tell us what kind of weights that contributed this kind of error, and it's going to reduce the weight so that the weight that causes the error will be reduced so that it doesn't trigger the activation function. And this is the best part of it, right? Because by using this method, we know what kind of weights to update, what kind of weight to reduce, what kind of weights to increase, so that the neural network know exactly what kind of patterns to learn. And this is the whole idea of the backpropagation here. And I would highly suggest or strongly recommend you to go and look up more about how the partial derivative work. Okay, although the terms here sounds a bit technical, but the fundamentals idea behind this is really to know exactly what kind of weights to update for each of the iterations here, so that we can continuously minimize the error for each of the iteration. Okay, you can think of this like a human. We as a human, as a children, how do we learn? In the beginning, right? We make mistakes, and our teacher is telling us, hey, you make mistakes for this part, this part, this part. Now you need to make change. You need to know where you make your mistakes. You need to know where to change, where to improve in order to increase or improve your grade. So this is the whole nature of the learning and teaching part. And this is the same for our neural network. Neural network is like a child. It keeps learning and learning and learning, okay? And the loss function is like a teacher. The bigger error that you have, and then this loss function will tell the network, or the backpropagation will tell the network, hey, you make this kind of mistake. And this is telling the weight to reduce it, so that the network itself can learn the proper weight, can learn the proper pattern among itself, and this can update the weights accordingly. Okay. Now, here comes the best part, the example of how we use this in real life. Imagine now you have Alexa, okay, or the voice recognition device. Now the task here is really to learn how to discriminate between two different voices. Let's say saying hello. Now imagine you have two different sources by Steve or David. They have different frequencies. Now your task is to train a neural network to determine what kind of sound source belongs to Steve or David. Okay, just assume that you now have a feed-forward network. You have 60 inputs, and each of the input refers to a frequency bin, because sounds is a frequency, right? And then we have 6 hidden layers, like this, 6 hidden layers. And we have 2 output. The 2 output here refers to Steve and David. Okay. Now, without understanding anything, without training the neural network, what are the errors? For an untrained network, for Steve here, without training anything, the Steve here we can reach maybe up to 26% of the accuracy. Or maybe for David, the accuracy is quite low because we can reach about 73% of our accuracy without training any neural network. Now, for the first round, this is the weights, this is the output that we have in our output layer. Once we calculate the error by minusing all these 0 and 1 here for each of them, we can see the what? The error here. So what is the error? The error for Steve is 1.17 and the error for David is 0.82. Now, it seems like the error of the prediction for Steve is higher than David. What does that mean? That means that some of the weights from Steve is wrong. So it means we need to fix it. And using the backpropagation method, we know exactly what are the weights that we can need to update, need to fix it, and to reduce the error here. And we repeat this process for all the training pairs, right? Recall that we present the data. After that, we propagate the data throughout the whole network, and then we calculate the error. Once we know the error by using the loss function, we then backpropagate this error back to the whole neural network, and then we adjust the weights. And we repeat this process for multiple times. And each of the time is what we call one epoch. If you heard people say, I want to train this network to 100 epochs, that means this neural network is being trained for 100 times. That means this neural network is being updated, the weight is being updated for 100 times. And this is how many times that the neural network has learned. Now, assume.
Yeah. Hi, Admin.
Now that we have trained.
Sorry to interrupt.
Yep.
Can you please go through this example once again? I think it went a little fast. The voice recognition example of differentiating between Steve and David.
All right, sure. Thanks for letting me know on these parts. Okay.
Yes.
Okay. Here. Right?
Yes.
Hello? Correct. Cool. Okay, I think let me maybe explain in a slower pace or in a clearer way. Now that we have a task, our task is to train a neural network to learn how to discriminate, how to distinguish between two different voices of saying hello. Okay, so just imagine now you have two kind of data sources. First from Steve, another one from David. Each of them is saying hello. Okay, and because we know that sound has a frequency, so our data source is really a different frequencies here, distribution as you can see here, right? And we have different frequency distribution. For example, here we have 60 bins. So that means we have about 60 features. And each of the feature refers to one frequency. All right. So the whole objective of doing this is really to help us learn which source belongs to Steve and which source belongs to David. That's it. Okay. And we're going to train a network to learn how to determine different voices. For example, now I give you a voice saying hello. The neural network must be able to tell me who this hello belongs to. Maybe it belongs to Steve, maybe it belongs to David. We are not sure. That's why we need to feed the data in, train the model, train the neural network, and this network will learn what kind of data sources, what kind of sound sources that the frequency belongs to. Just imagine, now we have a very simple neural network. Again, because we mentioned that each of the inputs is a frequency, right? And this is in the input layer. So for this input layer, we have 60 inputs. We have 60 different frequencies. Okay, it's a row of data, 60 frequencies. Now we input these 60 inputs, 60 neurons into our inputs layer. And now, just to keep things simple, we have 6 hidden neurons within our hidden layer, right? So the first one is input layer. Second one is the hidden layer. And this hidden layer, we have 6 neurons. It could be 7, it could be 8, up to you. But to keep things simple, just put at 6, right? Now, here comes the final layer, which is the output layer. Again, recall that our aim here is really to determine what source that the frequency belongs to. Let's say I give you a source of hello, the neural network should be able to tell me this hello belongs to Steve or David with a good accuracy. And this is the whole idea of training the network to help us identify who this hello belongs to, right? We only have Steve and David. So we need to tell, okay, this source belongs to Steve, or maybe this source belongs to David. This is the whole objective of training a network for this particular case. All right. And just for the first time, we have an untrained network. Untrained network here means that we haven't gone through any iteration. We haven't gone through any learning journey. We haven't gone through any process of updating our weights here. It's literally an untrained network. Nothing changed, no error updating, that's it. Okay. And for the first time, let's say we feed in the frequency here. You can see there's 60 inputs here for Steve and David. Okay. We know that in actual, the ground truth is that this source belongs to Steve and this source belongs to David. We know that. But what about the network? Does the network know that? And we need to train that to learn that, right? So we feed in the data to the network itself, and then we will feed in, do all the multiplication that we talked about just now, and then we trigger the activation function here at the hidden layer, and then we're gonna output us the values here. Okay, and the hidden layer here could be any activation function. So for simplistic understanding, we just use a linear function. Hence, the output here could be any values. Could be 0.4, 0.5, 0.6 upwards. Okay, but to keep things simple, it's really our whole goal here is to minimize the error throughout the learning journey of this network. Okay, so it doesn't really matter what these values here at the output layer refers to. Just know that we want to minimize the error of this output layer, and that's it. And for the first time, this untrained network gave us 0.26 for Steve, because Steve is what? Steve is 0 to 1, right? That means the second neuron refers to Steve. The first neurons refers to David. And if you look at this is 0, this is 1. This is 0, this is 1. So 1 refers to Steve, okay, for the second neuron. And 0 refers to David here. And we want to classify which source that this frequency belongs to. And for the first time, this untrained network only gives me 0.26. It's kind of low value, 0.26 for Steve. Whereas for David, it gives me 0.73. All right, but we still don't know the error yet. So we're going to compute this error with the ground truth that we know. We know that 0 refers to David and 1 refers to Steve. Okay, so now once we calculate the error by finding the difference between the predicted values here and the output values here, we know the error. Okay, the error here. And we take the difference of this error, getting the absolute value. This is the error that we get. And this is the error that we get for David as well. So what do we do next? Once we have the error, the next thing that we need to do is to tell the network to update the weights, because some of the weights are doing it wrongly, all right, causing the network to learn something wrong. So in order to minimize the error, we're going to back propagate the error to the network itself and to update the weights so that the weights can be updated accordingly to learn a better pattern, okay, to learn how to identify a better source by giving in the frequencies. And the whole process of this is a few steps here. We're going to do by feeding in the data to the network, as we just showed earlier. And we're going to calculate the error at the end, which is this. Right? The red colors here refers to the error. And we're going to back propagate this error back to the network here to adjust or update the weights. Once we adjust the weights, we're going to find the error again. So that means for the first time, yeah.
There's a common confusion arising about what the two outputs mean of each example. Like what is the first output representing and what is the second output representing? Also, like there's another confusion about
Yep.
like if the probability ranges between 0 to 1, then how are the like values above 1 here?
How the probabilities refer. So your questions is on the
Yeah, first
outputs.
is on the outputs about what each output actually represents in each of the example. Yeah, so as we have two
Mm,
outputs in the
yep, yep.
final layer. Yeah, so this
Okay.
if you can like provide some explanation as to what each represents, it'll be great.
The 0 to 1 here, right? Is that what you means here?
Yeah.
I think we can think of it as a probability here. So in this network itself, it is like a classification, right? Classification. Either this is Steve or David. That's it. So we want to determine in this output here, there are only two things here that we care about. Either it's David or Steve, right? And to classify these two things, we just assign a number here, which is 0 to 1. Okay, 0 to 1. And the whole calculation here, originally the meaning behind the values here, the value that you are seeing here, the output value here, okay, can be referred to as a probability, But to keep things simple, I just get the difference between these, right? And then I just sum this up to find the final error here. The final error here. So the error here doesn't mean that the probability is more than 1. The error here simply means how big is the error in the network itself. So you can think of this value, not on the probability side, but more on the error side. The higher the error, that means the network is something wrong, and we need to adjust the weights accordingly. Does that make sense? We can think of it, the error here, as really just a magnitude, a value. Like this error, if the error is 2, so that means this error is pretty huge, and we're gonna change the weights accordingly. Whereas if the error is lower, about 0.82 something, so that means I still need to adjust the weights. Maybe I need to adjust the weights somewhere else in the network itself, and that's it.
So,
So
can you explain why we are subtracting 0 from in the first example, Steve? We're subtracting 0 from the first block and 1 from the second, whereas it's opposite in the second one.
Great question. So if you go back to the first slide here, right, we show that to determine if it's Steve, we assign 0 and 1. So that means, let's say this is Steve, right? Steve is assigned to 0 to 1. So that means this is for Steve. 1 refers to that person, right? I just randomly assign for the second neuron in the output layer refers to Steve. And the first neuron, which is this, at the output layer here, refers to David. This is meant to help us to know which neuron refers to which person, and that's it. And that's why you see that for Steve here, on the second neuron in the output layer, I put it as 1. Because I want to use this value to tell the neuron that, hey, you are adjusting, you are giving me a lower weight for Steve here. Something must be wrong here, which gives me a higher error, which is 0.74, right? And that's why with the higher magnitude of the error, now I know that my network is not good at classifying Steve, and something must be wrong within the network. I need to go back to update my weights. And that's it. Yeah.
Yeah, I guess it's pretty clear now.
Yeah.
I'll let you know if there is any other. Yeah, there's one question.
Sure.
If there is an error, so will the weights of both the input and middle layer be changed? And how will the model understand which layer to change weight of?
Sorry, your first question was if there is, sorry, what?
If there is an error, so will the weights of both input and middle layer be changed?
both the middle layers and the
Basically,
input
the
layer.
hidden layer and the input layer.
Oh, right. Only hidden layers will be changed. Input
Yep.
layer, we won't touch any of the values in the output layer and the input layer. We only change the weight in the hidden layer.
Mm-hmm.
Yeah,
And
because, yeah, sorry.
and how will the model understand which layer to change the weight of?
How do the model understand which layer to change?
Yeah, the weight of.
Yeah, okay, so I think I get what you mean. To understand how each of the, okay, so currently we have one hidden layer, all right? So in order to know exactly for each of the neuron, what kind of weights, which weights that I need to update and how much that I need to update, this is the core algorithm done by the back propagation here through partial derivative. And if you look at this formula here, without going further technical explanation, this is telling me that for each of the weights here, I will have a learning rate, which you can see at the symbol here. And this is telling me that the whole
I
idea here is
guess
telling
you need to enable the cursor. We can't see your cursor, so we don't know which
oops.
formula you're pointing to.
Can you see my cursor here?
Yeah, now I can.
Okay, sorry. Okay. All right. So let me put the pointer here. Is it better?
Yeah, perfect.
Cool. So now this is back to our previous slide, which is the back propagation. Previously, we mentioned that this is done, how the weights are updated is done through a method called partial derivative. So back propagation is a process, and how this is done within the process is through partial derivative at the very core. And the partial derivatives here happens at this kind of formula. Okay, so this is telling me that for each of the weights, which is W1, how much that I need to update. Okay, look at this derivative here, del L del W1 is the whole formula of this, right? Okay, and let's don't care about what this formula does, but the end result of this formula is telling me how much weight that I need to update, either through positive or negative value for this formula here. And this symbol here is what we call a learning rate, how fast we want to update the weight, how big of the step that we want the model, the neural network to learn. Combine this both together, we now know how much change or how much weight that we need to update for each of the weight here. And this results in the updated weight as the updated W1 here. Okay, and in this formula itself, the del L del W1 is the partial derivative of the loss function with the change of our predicted values and multiplied by other values here. So the whole idea of this is really to know how much of the change that we need to make to each of our weights here, either minus off it through certain values or adding some more values to our weights. If we find that W1 is important for the neural network to learn certain pattern, this calculation will give us a negative values. Because why? Negative minus negative is positive. So this W1 at the end will be a summation of W1 plus some values. And this will give more weight to the W1.
Yeah, I guess the maths will be a bit overwhelming for the beginners to understand.
Yes, yeah.
But
yes.
yeah, we do get the overview of what you're trying to say. Yeah. Also,
Cool.
there's one common doubt about why there are two outputs when the problem is to recognize only one voice. So, like, it should be either of Steve or David. But why are we getting two outputs?
You're asking about, okay, let me change
The example.
this. Yeah, the example. Oops. Okay. For this.
No, I think on the next slides,
Yeah.
maybe. Yeah.
Okay. Yes.
No, after this, maybe. Yeah.
Yeah, this.
Yeah, here.
Right.
Yeah.
So the question is, why do we have two outputs here?
Yeah. So basically, like ideally, we should have one output which tells us if it is David or Steve. But why are we getting two here?
Basically, there are two outputs. Yeah, correct. You are right. Essentially, in real life, we should have only one neuron here. Either is between 0 to 1 here. But to help me illustrate the point of classifying whether it's Steve or David, I just intended to put two neurons here to put this more explicit in a way that we know that this neuron at this output layer here belongs to Steve. And this neuron at this output layer here belongs to David, and that's it. And by doing this, I want to explain it more explicitly as to, if you just look at this second neuron here for Steve, we know that this second neuron is telling us whether it's Steve or not. And now, if we minus this by 1, we know that this is Steve. This sound belongs to Steve. And if we minus this 1 here, get the absolute difference. We get the value here. And the higher the value here means, the higher the error. So that means that given the fact that we know this sound belongs to Steve, but still, I still get a higher error here. So that means something must be wrong with the weights. I need to change that. But you are right. In order for the binary classification, usually we have only one neuron from 0 to 1. But to make things more explicit here, I purposely split them into two neurons. Just for one for Steve and one for David. Just for you to see that one here at the second neuron refers to Steve, and the one here at the first neuron refers to David. That's it.
Yeah, I guess that's perfectly clear now.
Yeah, and I'm sorry for the confusion of splitting these neurons. Yeah, okay. All right, any other questions on this example here?
No, I don't think we have more questions right now. You can move forward.
All right, yeah. Back to the original the sharing here, which is once we have trained the neural network for multiple times, we keep adjusting the weights here. Assume that we have finally trained a good network, a good model. Now we have done a pretty good accuracy here. You can see that 99% of the time we are able to identify that the voice here is Steve. And we also identify that the voice here belongs to David, given the frequency of all the distributions here. So this is the whole idea of training whole neural network from scratch, given the fact that we feed in the data for the neural network to train and to update the weights accordingly with different iteration. And then we can try to minimize the error. And finally, we want to improve the accuracy of our prediction. So that is the whole, I would say, the whole general process of how a neural network is trained. And if in case you want to know how exactly the neural network trained in real time, I highly recommend you to, let me go on this part if I can place it. Okay, to this link here. And if you just go here, I think you can go it right now. It's a Tensorflow Playground. You guys can play with different parameters here. Learning rate, activation, what kind of activation function they use, and also regularization, which I'm going to talk about it later on. What kind of problem type that you want to solve, and just click it, and you can see how the neural network is being trained from nothing, right? Here we have the input layer. This is the hidden layer that we have with 4 neurons. This is the output layer, and this is how the neural network has learned based on the number of epochs so far. You can play around by adjusting the weight here, all the different parameters to have a sense or intuition of how the neural network is being trained in real time. Okay, so this is just for you guys to play around and get a hands of it. So without that, let me get this back to the Carrus part. So here now we have understood how the network works in general way, and how to train the neural network from scratch by feeding the data, get the error, update the weights, minimize the error, improve the accuracy. But how to do it? here comes the question, how can we implement the whole training process of the neural network? And in the industry right now, the common tool of doing this is through Carrus. And in case you are not aware of this tool, I would just want to give you a brief intro to Carrus in this session so that you know exactly what to expect. So Carrus is a high-level deep learning API written in Python that can really run on top of different deep learning libraries, namely TensorFlow, CNTK, Theano, etc. TensorFlow is one of the most popular tools on top for Keras to use. And in a layman term, Keras is really just a Python deep learning library. It's just a library, nothing much. And basically, it is an API for people or human beings to use without too much technical things to do. So if you're just starting out as a beginner in deep learning or understanding neural network, I would highly recommend you to try Keras as your first deep learning library to get a hands of how to build the network layer by layer and how to reduce or improve the accuracy. And TensorFlow is an open source deep learning library developed by Google. I think it is one of the most popular tools right now being used in the industry. And when the TensorFlow 2.0 was released, it adopted Keras as well as the official API. So now, as a developer, as a data scientist, we can import Keras directly from our TensorFlow library. So it's a combination of both together. It's the best in both worlds, if you think of it. It is a marriage between TensorFlow and Keras for people like us to do deep learning modeling. That's it. So why Keras? Because it is easy to use and it provides simple API to build deep learning models, as mentioned. If you just go to read out some of the documentation, it really provides a very clear and actionable error message for people to debug. Also, it is easy to test new ideas because it's so easy to build a network without too many technical involved. We can easily build a prototype models and deploy it to production. And these are all easily supported in Keras itself. Also, if you want to learn run some heavy neural network in your GPUs or other clusters, Keras can support that as well. And this is widely adopted in our current industry and also the research community. If you go to Kaggle right now, Keras is, I think, the top machine learning software tool being used by some of the top 5 teams. And this survey was done back in 2019. And I believe Keras is still widely being used in the industry. So now here comes the core part. Now we understand how Keras works. Why do we need to use Keras? The third part to know is how do we use Keras? How do we get Keras? Okay, with the latest release of TensorFlow 2.0, I would suggest you to just install TensorFlow using the way here. Pip install, upgrade your pip first, and then just install the stable release for the TensorFlow. And once you have installed the TensorFlow, just import the TensorFlow to your notebook or whatever IDE. And then from there itself, you can just use Keras on the fly. Okay, so now I just want to show you real quick on how to use Keras to build a very simple ANN model and see how that works. Okay, let me show you real quick. There's cool. Now this is the Jupyter notebook, and I've pre-run the code so that we don't need to wait for the output to come out because it takes a bit of time for us to run some epochs or iteration to train the model. So here we just really go through some steps on how to use Keras and train the model, and that's it. So here the idea, the problem that we are solving here is really we want to predict whether the house price is below or above a median value, and that's it. We want to train a network to help us predict whether the house price is below or above our median value. Okay, and then we're going to use a few steps here. First, we will explore and process the data. Second, we're going to build and train our neural network. And third, we're going to visualize the loss and accuracy because we need to know how the metrics are going on behind. And finally, we're going to add some regularization, which is to simplify our network to improve the accuracy. And you can get the data set here. And this notebook, no worries, you'll be getting this after this session. And first of all, as usual, we import the pandas.
Admin, can you please zoom in a bit?
Oops, sorry, sure. Is it better now?
A little more maybe.
Yeah, sure.
Yeah.
What about now?
Yeah,
cool.
Thank you.
Sure. Now this is how the data set looks like. It's pretty simple. It's all just numbers. If you look at this, we have the lot area, the area of the space, some of the numbers here, which you can see from the data set itself. Or it's the size of the bedroom, etc., etc. All these are numeric numbers, which is cool because we don't need to do any other modification. And just to keep things simple, we get the values from the data set, which is this, put them into arrays. And if you look at this data set, all these are our features. The final column here is our label, which is this column is telling me whether this row is above median price or not. Okay, and this is what the network will be learning from the features. By feeding all the features in to all the neurons here, the network will be able to tell us for each of the features here, each of the row here, is this house above median price or not? This is the question. And the neural network will be able to tell us by training it. Okay. And this is the data set, and we're gonna just get the data set out. Okay. And usually in neural network, it is important to normalize our data because our data, if you look in this way, it has different range for each of the column. For example, lot area here, we have the range in thousands. For example, for the full bar here, we have the range in terms of just a single digit. So in order not to skew the learning of the network itself, usually it is highly recommended to scale our data, our features to a common scale, 0 to 1, for example, for each of the column here. Meaning that for each of the column here, each of the feature, we're going to scale the values here to 0 to 1. Okay, it doesn't matter whatever range here that I have. I just want to scale each of the column here to from 0 to 1. That's it. And I do the same thing for each of the feature here. So that at the end of the day, each of the feature here ranges from 0 to 1. And then I can fit in all these features to our network to learn. It is simpler to learn because it is just 0 to 1 range, right? And we use a library called min-max-scaler. And this can be used or imported from our favorite library called scikit-learn. So we import this, we use a library called min-max-scaler. We scale this into 0 to 1, as you can see here. Now, once we scale the data and we have our data ready at this point of time, we're going to split the data set. By now, we should have already known that usually in machine learning or deep learning problems, we want to split the data set into training, testing, and validation data sets. And this is what we are doing here. We're going to take 70% of our data as our training sets, 15% of our data as our validation sets, and 15% of the data as our testing set. That's it. 70, 15, 15. Cool. Now, we have our data ready. We have already split our data to the ratio that we want. Now it's time to build a network. First, we import the TensorFlow. And from the TensorFlow, we import the Carrus library. It's cool. Carrus is now embedded within the TensorFlow. And from the Carrus, we import the layers. And just a simple layer, right? Just a simple network. Now we're going to build the Carrus layer by layer, the network layer by layer using a sequential library here. Sequential model here means we're going to build this layer by layer, okay, in sequence, hence the name sequential. So here we're going to build essentially two layers, two hidden layers, one output layer here, okay. And just to keep things simple, dense layer is all the highly connected layers to each other. And within this layer, let's say the first hidden layer, I'm going to have 32 neurons. And for the activation function, I'm going to use ReLU. And ReLU is just one of the most famous activation functions. And you can sort this out or maybe understand better by just going online and understand what ReLU means. But for now, let's take it as a part of our activation function. So we use ReLU as our activation function. And also same thing for the second hidden layer, exactly the same, nothing changed. And for the final layer, the output layer, we're going to put in the sigmoid activation function, which we already knew earlier. Okay, the sigmoid is essentially just an S-curve to tell us whether is the probability, And it's a pretty simple neural network with 2 hidden layers and 1 output layer. Now, since we already have our architecture here, this is our architecture. Now we want to find the optimizer. What kind of optimizers, what kind of loss function that we want to use for the next step. Here is the time that we need to compile the model. Here we define the model. After we define the model, we need to compile them into an object. And here, the optimizer here, we use stochastic gradient descent. Okay. And it's just one of the optimizers that we usually use. And if you want to understand more about the stochastic gradient descent, maybe you can do it in the Q&A later. But due to time constraint, let's take it as it is. This is one of the optimizers that we are using. And again, the loss function could be any loss function. It could be the MSE or root mean square error, or because we are solving the classification problem here, so we use a binary cross entropy. Regardless of what this means, this is one of the famous loss function used for classification, specifically binary classification. Okay, and because we already have the metrics here, but let's say you want to track other metrics as well, maybe accuracy, maybe precision, maybe recall. You can add in the additional metrics to train the model here at these parts, right? Now, since you have already defined the model, compile the model to the way that we want, the next step is to train the model. And to train the model is pretty simple. Just dot fit with the training data and the batch size that we want, and the number of iteration. Here we put as 100, and the validation here. So what this means is that for each of the batch, okay, so here the batch size is 32, means 32 rows. I consider each batch here, you can define 64 or 128, it's up to you. But to keep things simple, let's put it as 32 here. Imagine for the first batch is 32. I have 32 rows coming in to feed the model. And I'm gonna do this iteration, the training part, for 100 times before I update my weights. Okay, so now once I've have the error here, updated my weights, I'm gonna compare this prediction accuracy with my validation data, which is the 15% of my data set that we split earlier. And we're gonna compute the loss and accuracy as well, as you can see here. Okay, now here we are doing like 100 epoch here. If you just scroll down, each of the epoch, the loss is slowly decreasing, the accuracy is slowly increasing, right? And finally, we reach the 100 epoch here, and we have about 0.28 loss, about 0.9. Accuracy seems not bad, but by looking at the epoch here, it is hard to know the whole process of the training journey. And that's why we need to plot this out to help us understand how the training process works. Is it doing good? Is it doing bad? Correct? Now, once you have the model, without further ado, we now want to evaluate the model's performance by comparing the prediction values with our testing data sets. And again, this testing data set is the final 15% of the data set that we split earlier. Okay, now that we have trained the model has to learn something, how to determine the house price. Now with the predicted values, we're gonna evaluate this with our testing data, and that shows us that the model is able to reach about 85% of accuracy. Not bad, right? Not bad, without doing any optimization here. But to further understand exactly how the loss and accuracy works behind the scene, we're gonna do some plotting here. And this is common for most of the training part. Once we do the training, once we do the testing, we need to understand how the training works by visualizing our metrics, which is accuracy here. So now imagine now we plotted this thing out. We want to just visualize the loss of our models here for our training data and the validation data, we can see that it's pretty good curve, because as we go through every single epoch, the training and validation loss here tends to decrease together, which means that we don't have any of what we call overfitting issue. Overfitting here really means that the model has learned so much from the training data that it tends to not be able to generalize well when we use the validation data to test the model. Okay, here we really don't actually see the overfitting issue here, which is good. But what about the accuracy here? If you just plot out the accuracy here, again, we are looking this between training data set and the validation data set. It's pretty good because we don't see the overfitting issue here. You can see that the training data and the validation data is increasing together slowly, which is cool. And again, this is the whole general process that we use to evaluate how well our metrics are doing behind the scene, to really understand whether there is whether our model has learned well or not. If you want to go a step ahead, you can even add a regularization to our network. This step is only done when you think that your model is overfitting, when you think your model is too complex. Now you want to simplify your model, your neural network, by regularization here. Okay, and I'm not going to go through this again. This is just another layer here, another neural network. I just make it too complex, and then you can see that it's overfitting now. So this is another neural network. I just anyhow make this up with so many neurons here, so many layers. And again, as expected, if you train this model, these complex models here, it tends to overfit with the data, as you can see in the loss function here. If you just look at the loss metrics here, if you compare this between training and validation data, you can see that as our training goes by, our loss is decreasing, which is good. But our validation data shows us something else. It shows that the loss is increasing. So what this means? This means that the neural network has learned so much from the training data set itself, to the extent that the model is not able to predict well when we give them the validation data. Okay, so this means that usually when you see the curve here for the validation data set, it means that there is a chance of overfitting, whereby the neural network is too complex. Maybe there are too many layers. Maybe there are too many neurons here. We put 1,000 neurons here, which is crazy. So this means that we need to do some sort of regularization by simplifying the model. Question is how? We do this by using another parameter here called kernel regularizer. All right. And there are two types of regularization here, usually L1 and L2. But regardless of what this means, the whole idea here is to reduce the number of neurons that we have in our layers, and to put some parameters here to regularize our network. And the whole idea of doing this is really to simplify our network. That's it. Make it simple, such that the model wouldn't learn so much from the network, from the training data set. And then once we use the method here, once you regularize the network, now it makes sense. If you look again at the loss metrics or the accuracy metrics here, we no longer see the curve here on the validation data set, which is good, because now we are sort of able to make the network simpler, and then the model is able to predict well when we put in the validation data set. Okay. Again, as compared to model 2, you should see there's less overfitting now. And if you want to go further a bit, there's a next step for you to optimize the parameters in the network, which is not covered in this session due to time constraint. And yes, again, this is the whole process of doing the training using Carrus to train a neural network by exploring the data, scaling the data to the scale that we want, 0 to 1, building the network layer by layer, and then training our network with the metrics that we specify. Then we visualize the loss and accuracy to see how well our model has learned, or how bad our model has learned, to see the performance, and see how to tune the model. So the network learning is not one-to-one. It's you need to tune the models multiple times to reach the performance that you expect. And this is the whole the process of building a network using Carrus. Now, let me show you this. Okay, that's it. I think I have already given you a better idea of how network works and also how to implement artificial neural network, simple network using Keras. And I hope that this session is able to get you started using Keras or TensorFlow to build your own neural network using your own local PC as well. And I hope this session is helpful to you so far. Feel free to connect with me either on any of the social medias here, and feel free to ask me any questions if you have on any of these platforms as well. Thank you.
Yes, thank you, Adnan. That was like really insightful about. We have not yet discovered this part of data science in the bootcamp till now, and they was pretty new and pretty knowledgeable. And it's actually nice to explore the different domains that we have in data science itself. So I guess we can address a few questions that we have.
Sure.
Yeah. So some people had doubts about what batch size exactly is and what batch function does.
Let me go back to this. I do have a batch size here, by the way. Let me search, right? For this, correct? So your question is, what does the batch size here mean, right?
Yes.
Okay. To illustrate the point here, maybe let me pull out the data sets. Maybe not this, maybe this. Okay, so the batch size that we specify here is 32, correct? So the 32 here really means in the dataset itself, if you go back to the dataset, this is the original dataset. Batch size of 32 means there are 32 rows of data. Each of this row of data, imagine this is 32 rows of data. For each of the time to train the model to update the weights, I feed in 32 rows of data to the neural network and start learning, because I can't feed in the whole data set for the neural network to learn. Otherwise, it will be a huge sum of multiplication of metrics, which will cause heavy computation, and it doesn't help the neural network to learn. So in order to help it learn better, we usually split it into different batch sizes, either 32, 64, 128, up to you. But here we split this into 32 rows of data for each of the learning for the neural network itself. So once we are done with the 32 rows of the data or each batch, we move on to the second batch, which is the next 32 rows of data, and we feed into the neural network again and update the weights accordingly. Why do we do that? Because by splitting this into many batches, we can help the model learn better by constantly updating the weights. But just imagine you don't want to split into many batches. You just want to put in the whole batch, right? Let's say you have, again here, if you see, we have 1,460 rows. Imagine you're feeding the whole batch number of rows here to the neural network. Now the neural network can only learn one time. Just imagine, okay? It can only learn one time by adjusting the weights, and that's it. It cannot learn further. Okay, so the mini batches here is really to break it down into different iterations so that the neural network can update the weights more by learning the features from the data set to give us a better prediction and to give us a lower error from our prediction itself. Yeah, and to make our computation much faster. If you have 1 million row of data, you feed into the neural network, your PC is going to crash because your 1 million rows of data could consume, not sure, maybe 4 GB or 8 GB of your RAM of your PC. And usually if you feed in so much of the data at once, our PC is going to crash. Yeah, and these are some of the reasons why we use the batches here.
Yeah, clear.
Yeah.
Also, can you elaborate on what epochs mean?
Okay, cool. Let me go back to the slide. Previously, we mentioned there is a thing called epoch. This. Okay. Yep, this is a slide. So what epoch here means, epoch is kind of a strange term, but to understand it, one epoch is one round, if you would say, or one iteration. But how do we consider as one epoch? Here, let's say the first time I have a batch of data, okay, I input to the input layers here. Maybe let me change this to parent. I have a batch of data. I input to this input layer here, and then I do some computation with my hidden layers with the weights, okay? And I have some output in the output layer here. Now, I compare the output layer values with the actual values. I compute the difference. I use the backpropagation, go back to my neural network to update the weights. This whole back and forth thing is considered one epoch. Okay, one way is half epoch. Nobody call it half epoch. Usually when we say one epoch means we have a batch of data, go to the input layer, do some computation, give us the output, we backpropagate back to the whole network, update the weights, and that is considered as one epoch or one training round.
Yeah.
Does that make sense?
Yes.
Yep.
Yes.
Sure.
Also, someone asked where to use which activation function. I guess that's
Right.
a
Yes.
detailed topic, and might
Exactly.
be able to cover it here. Yeah.
Okay. Remember just now I mentioned that the activation function that we use here is ReLU. So what does ReLU here mean? ReLU activation means is the full name here is a rectifier function. And if you just go and Google online what is ReLU, you will see essentially it is a linear line. Okay, it's a linear line. So if you ask me what is the common activation function here, I would say the best practices here. Usually in the industry, we would use ReLU as our activation function. Why? Because this will constantly helps us to help the network learn the pattern without facing the gradient problem. The gradient problem. Because if you use other activation function here, there is a chance whereby the activation function can no longer help the neural network learn or update the weights anymore. Or what we call the gradient explosion. It's another topic, by the way. But to make it simple, the common activation function here is ReLU. Yeah.
Yeah. Great. I guess almost all the doubts have been covered now.
Yep.
Thank you so much, Admond.
No worry.
Yeah, I believe Chanukya would like to say something as well.
Sure.
Yeah.
Yes.
Hi, Admond. Thanks.
Hi,
First of
Chanu,
all,
yeah. No worries.
thanks a lot for the session. I was
Yeah.
listening at the other end as an audience, and I
Yep.
think it was very insightful. Thanks a ton for that. And on the other end, I have a small message to the learners. So first of all, I would like to thank Julian at the other end. He has been trying to respond to all the queries and moderate on YouTube, and thanks to Gunika as well. Yeah, so here is a quick update for all the learners. So far, I think we had already come to the end of fourth week, and it is a very long journey already. And we realized that some of the people are facing issues with model building and bunch of other things. So we'll be having a doubt clearing session in the next week. And next week will be a relatively relaxed week where we will be emphasizing on what we have learned so far, and we will be re-emphasizing on some of the topics and probably solving a lot of problems, so that that would solidify some of the concepts that we learned so far. And also it will help us to basically apply those concepts in the real world by playing with some data sets. So that's some heads up for you. So it will be a very relaxed week next week, and we'll be solving a lot of problems. That's some update from my end. And Yeah. And apart from that, Edmund, so how are anything that you want to add to the audience? So generally, we have come a very, very long way. Now, I think people are struggling a bit to build what kind of model to build, or what kind of evaluation metric to use. And often, people also get confused at this stage where, I think this is a very confusing thing. Why do we need to, um, separate input and target variables in Python? Okay, train and test data set split, they still understand, but how did you overcome all these challenges in your data science learning? Can you maybe if you can address it, that would be great. How much time did it take to understand all these jargons? Yeah, go ahead.
Yeah, I think great question here, Chonu. Yeah, I think of course there's so much to learn, in understanding the neural network and also in the implementation part. And I really feel that because I was confused sometimes last time, and even now today I'm still learning some of the terms, how it works, and some of the jargon. So I would say that it is a continuous learning journey, but don't force yourself that hey, I'm gonna learn all the stuff here within 1 or 2 months. I would say it is highly impossible, but try to get yourself comfortable with some of the common terms, at the very least, common terms that we use when it comes to building a neural network. For example, ReLU. What does ReLU mean? Right, the activation function. What does ReLU mean? And there are some of the jargons or common terms that I would suggest you, the learners here, to go and understand further as another step here. A few things here. First is what is gradient descent? Second is what is backpropagation. Third one is what do each of the parameters of the neural network mean, like learning rate, like the optimizer. Okay, I didn't go deep into that just now. Optimizer, stochastic gradient descent, and other optimizers. Usually the metrics, there are tons of metrics out there, but just need to remember some of the key metrics, like for regression, RMSE, root mean square error. For classification, usually is precision, recall, or ROC, or area under curve, AUC, stuff like that. So that depends on the metrics that you need to use. Highly depends on the problems that you're solving. So there's no hard and fast rule that you need to use this metric. No, that depends on your problems that you are solving, and that requires time and experience. So I can't really show you what exactly the metrics they need to use. That comes with experience. But these are some of the common, I would say, the common metrics that we use when it comes to building a model. And I would say that don't deep dive too much into the technical jargon. Just gain a better understanding, a high level understanding of all these technical terms that I just mentioned, and go straight into the implementation part. Once you start building the network, you would know what are the problems that you're facing. You will go and Google for resources, ask your friends, hey, how should I improve my prediction stuff? And you get all sort of suggestion or advice. And this is where you dig deeper to understand, why do I need to change this parameter? Why not others? Stuff like that. So that takes time. I will highly you to the learners here to really read more articles on Medium. I think Towards Data Science is a great resource. There's tons of resources out there, KDnuggets, or even watch some of the videos out there by kind of a prominent data scientist on LinkedIn or on YouTube. Yeah, to learn some of the best practices out there. We can't learn alone, but we can learn from others in the data science community. And usually for me, I would prefer LinkedIn. They have a kind of huge and supportive community. Usually the best practices or the latest trend of neural network, I learn from the experts out there. I'm not the expert. I learn from experts on LinkedIn specifically. So I would recommend you to do the same. Connect with the people in this field and learn from them. Yeah, this is how I would say.
Thanks a lot, Admond. I totally second that. I totally agree that the learning is a continuous process where, for example, there are so many terms, right? We only get it out of practice. And to be honest, even today, as you mentioned, you're still learning. Even I learn a lot of things, and sometimes even I have to go back and search what this particular term means, because I might have learned sometime in the past, and then I might have forgotten. So that is totally all right. And to be honest, I think I'm very proud that learners have come a very, very long way, and they're able to comprehend a lot of things, which is very good in my opinion. You just need to practice a lot more. It's all right if you're not understanding. As Admond mentioned, it's important for you to understand the intuition or the high level overview of each and every concept, and then apply them. Once you start applying, you see what the exact particular piece of code is doing, or what that particular algorithm is doing, and then automatically, out of this intuition, you will try to delve deeper and understand what exactly is going behind, be it the math or whatever it is. You will try to figure it out, because once you see the implementation part of it, once you understand the intuition, automatically you'll be curious to understand what goes behind. But that can happen at a gradual pace. It doesn't need to happen right away. You can do it in like, in few days time, or like, once you get a hang of the entire process, I think you can gradually get into the maths part and bunch of other things. It's all right to take it slow and go at a gradual pace. Yeah. Thanks a ton. And thanks a lot,
Yep.
Admin. And
No worries.
yeah. And again, like, we hope to see you again soon for some other sessions. But thanks a lot for your time. And thanks a lot to all the learners. Yeah. Great. Bye.